Hi, everything in the world are elastic to a certain extent. The rubber band, of course, is very elastic. My earphone string, not so elastic. My skin, very elastic, of course, and bouncy. A pen, not very elastic, but inside there's a thing called the spring, which is elastic. You can make it longer or you can compress it. So when we talk about elastic in physics, it's simply saying that when you exert a force, then they will deform. So probably they will become longer or shorter if you're talking about spring. Yeah, you can make it shorter. Well, for rubber band you can't. But then, yeah, for spring they can go in two ways. You can make it longer or you can make it shorter, and that is depending on how elastic they are. In 1660, a scientist called Robert Hooke investigated the property of a spring, and he actually found out a relationship like the graph that you can see on the screen. Because of this, he invented a law named after himself called the Hooke's law, simply. NANI? And this is going to describe the extension of a spring under a force. For Hooke's law, I would like you to fill in the blanks in this page and try to understand the concepts by yourself, and I will also recommend you to read the textbook for this subchapter. So please pause the video and try to understand this yourself first.
A few moments later.
Okay, so let me review the key points with you again. So first of all, the idea of Hooke's law does not really apply to everything and any time. It's actually only describe a certain material and at a certain force or length only. For example, the rubber band does not actually obey Hooke's law at all because they don't extend in proportion to your force. Spring, however, is something that obeys Hooke's law at the beginning, and so that is why here this is a graph that is based on the behavior of the spring that we use, but then we can only apply Hooke's law in this first part only. So for the later part, it doesn't obey Hooke's law anymore. And for the equation itself, you can see here law, or the so-called tension, will equal to something called spring constant times extension. So in terms of the symbol, we'll write F equal to Kx, or some people may use tension T instead, but I'll prefer F generally as a force because you can also compress it as a force. As for the extension, some people may use instead of X, they will use E, and both are fine, both should be acceptable. One thing, however, is you have to note that the extension does not include the original length in this equation. So that is to say, as an example, if we have a spring like this with x cm as the original length, let me put it down, you can also put it down as well, original length. And now if there is a block attached to it which would exert a force, which is the weight of the block itself, and therefore the spring, in order to maintain the whole system stationary, then there must be a force that pulling the block, and that is the tension itself. So since there's a tension, then there must be an extension, just like what I showed you earlier when I pull the spring. And so now this 11 cm is called the total length. And therefore, if you use the total length minus the original length, obviously you will get 3 cm. So 3 cm would really be the extension. So again, you can use either E or X to represent. If you try to attach a heavier mass, then obviously the force will be greater, and therefore the extension will also be longer, since the total length will also be longer as well. So in this case, total length is 24. And if 24 minus 8, then you can get 16 cm. So this would then be the extension in this case. Very intuitive. So that is to say, in the future, whenever you see a problem or a scenario you have to pay attention to the unit. So maybe the extension is given as cm and asking you to calculate the spring constant, then you have to be smart enough to know it is Newton per cm. Okay, so the length unit will be changed accordingly. And so for now, I have a question to ask you. What is spring constant actually? Would it change throughout the experiment, or is it universal? So is there a value for spring constant like pi is always 3.14 always? Or what does it actually depends on? Okay, let me give you more hints. I don't want to tell you the answer directly. So here is a simulation which probably in the next video I'll ask you to do. But then the most important thing is, again, we want to answer what is spring constant. So here I have got a mass. I can hook this up to the spring, and then I have set something called damping, so it actually means friction, so eventually it will stop. Even if I try to swing it, eventually it will stop at a certain position. That is the one that you want to find, and this is original length, this is the extension if you try to use a ruler to measure. But again, the most important thing is I want you to see the difference of spring constant, right? So here I have a control on the spring constant. I'm going to change it to small, and if you like to predict what happened, you can pause the video now. Okay, and now I'm going to change it. Okay, so try to observe the difference between the original and this one. I will also put down a link in the description if you want to try it yourself. Okay, now I'm going to the original, and again I will go to the other side, which is going to be a larger value of the spring constant. So again, if you want to make a prediction, try to make a prediction, and guess what will happen? In 3, 2, 1. Okay, so now I think you can answer the question that I asked earlier. So think about it again. Okay, so the answer is the spring constant actually depends on the spring itself. And you can see when I try to change it, you can see the thickness, okay, of the spring. Now it's the thickest, and when I change it to small, it's like the thinnest. And so from an experiment, you can't actually change it in practical. Think about this, like you can't magically change this spring or like make it lighter or heavier suddenly, right? Or thinner or thicker suddenly. So assuming you're using the same spring, then if you change to another mass, then it's going to be the same spring constant, of course, right? But then for the mass, of course, it could be different, and therefore the extension will be different. So putting this back to the equation, that means that normally for F equal to Kx, the K, which is spring constant, doesn't really change. And then you would change the mass, which affect the weight, which affect the force. So if this is greater, if you hang a heavier mass simply, of course the extension is greater. And so it's not very normal that we can change the spring constant directly. However, if you really do so in this experiment, simulation, we can also try to see whether or not these fit with what our formula predict. So here, if we make it large, then you can see the extension become less. So think about this equation, then we will have the force to be constant because we did not change the mass itself, and that means did not change the weight and did not change the force. But then if we increase the K, because we simply change to large here, right, which make it thicker. And of course, if you are using different material, for example, different metal like iron, copper, aluminum, steel, it would also give different spring constant as well, other than the thickness itself and maybe the configuration, etc. And so in this case, if you look at this equation, the extension will be less because to maintain the equation, in this equivalent state. And that actually match with what we see, right? When you make it the other way around, it will become longer. Making it bigger, it will be shorter for the extension. Okay, so now we'll talk about the general situation for the spring when we try to extend it even further. So let's refer to this graph and imagine someone did the experiment and plot this graph, which is Robert Hooke himself. And of course, you can also do the same graph as well if we are back in the laboratory. And so, like I said, the Hooke's law only is valid for describing the situation at the very beginning, and when the relationship of the force and the extension are in a linear relationship or proportional relationship. And because from the mathematical relationship, you can see F equal to Kx, just like Y equal to Kx, which is a proportional relationship, Y proportional to X. This is exactly the same idea in mathematics. So you can see afterwards, it does not really fulfill the idea, and otherwise it would go straight. I mean, if it's always having the Hooke's law correct. So Hooke's law is only applicable to this part, and you can see only up to the part which is called the proportional limit at this point. And so that is why here we will say as long as they are under their proportional limit or proportionality. And that is why back to the top here, you should have put down the word proportional limit, which is saying the Hooke's law would be extending according to Hooke's law. And some people may call it limit of proportionality. That's the same thing. Proportional limit, limit of proportionality, the same word. If we look further on the graph, we can see that the next portion will no longer be a straight line. So that is why this point is defined as proportional limit. And then the next point that you are going to meet if you keep giving force to the spring is that you will reach a point called elastic limit. And if you read the textbook, or if you ever perform an experiment, or in the future when you perform an experiment, you'll find out this elastic limit, and this is a point where the spring will not return to its original length. Okay, so basically you kind of destroy and deform the spring permanently. And this is very logical because think about this, you can never infinitely extend a spring, right, until it become a straight line. I mean, spring was like coil, right? And then if you try to pull it, you can't pull it infinitely. Eventually, sooner or later, they will just stay as that, shape, and it won't bounce back to the original length, and that is the elastic limit. And even the worst case, eventually, it will reach the point of so-called failure, and that means it breaks simply. So you can put down this would equal to breaking. And here I've got a question for you to think about what is the slope for this graph. And it's actually very simple because if you look at the graph, the y-axis is force and the x-axis is extension. So by just applying the general skills you learned in physics, then the slope, of course we are more like referring to the slope along this straight line, would equal to f divided by x, which is the extension, and that would simply be k. If you recall the Hooke's law itself, you just have to rearrange them around. And so that's what you can put down, equal to f over x, which equal to k, and that is spring constant. However, one thing I would like to remind you is sometimes the graph that is showing to you may be interchanging the axis. So that means you may have given a graph that is having extension and force like this. Okay, force is on the x-axis instead. So if you try to say, oh, there's a graph that is given to you like this, then the slope will actually representing E over F. And so in this case, the slope would then be 1 over K instead. So you have to be more careful about the label of the graph itself. Additional question. On top of the graph that I drew here, okay, I assume you also did that, I draw another line like this, okay, which is less steep than this. And let me just call this B and call the first one A. So my question is, which one is easier to extend? Alright, so there are two ways of deriving the answer by yourself. The first one is to look at their slope. So, I guess you all know that the slope of A is going to be steeper, and that means 1 over K value is greater. If 1 over K's value is greater, that means K of like spring A is going to be smaller instead. Right, this is just a mathematical relationship. So if A is going to be smaller, so K subscript A is going to be smaller, or I can write this, okay, which I think this is a better representation. Then if we refer back to the definition of spring constant, or by looking at its unit again, for example, if you have 1 Newton per meter, that means if you want to pull 1 meter, you need 1 Newton. Okay, so that means if you have a greater number, back to this one, with a greater number, you need a more force, a stronger force to pull for the same length. So that means for A is easier. So A is the one that is easier to pull, or to extend, I should say. Okay, it will extend more with the same amount of force, or it will extend the same length with less force. So this is one way of by looking at the slope to deduce the answer. The other approach which you can do is just simply look at the graph. And so let me zoom in a bit more. And you just have to look at, say, for the same force, okay, so I just randomly draw a vertical line. So that will mean it's the same force. So for example, this may be 5 Newton. And then you can look at the corresponding extension. So obviously for the extension B and extension A will extend more with the same force. So yeah, that coincides with what we find earlier, that A is easier to extend comparing to B is rather, not as efficient. So that is all for this video. You have learned about the Hooke's law equation itself, F equal kx, the unit, how does it actually define spring constant, what does it mean by extension and the original length, and also the definition of proportional limit and elastic limit, and how to read off from a graph like this. In the next video, we'll try to do this practice question, which will involve a graph also. I'll look forward to seeing you again in the next video. Bye.